بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 7.5, strategy for integration. You have to study well the first four sections, or maybe also chapter 6, substitution, the usual substitution, techniques for integration, to be able to uh, understand this section or go with it, because this section is only for students who studied the previous sections about integration. So let us remind ourselves with the rules of integration we studied before. So these are formulas we studied to find integral of x to the power n. And of course, we also said that you can write this formula replacing x by ax plus b. So you can find the integral of ax plus b to the power n, and you will use the same formula ax plus b to the power n plus 1 over n plus 1, but you have to divide by a, the derivative of ax plus b. So for example, the integral of x squared is x cubed over 3, and the integral of 2x squared is, well, 2x to the power 2, all of it, okay? 2x to the power 2 is 2x to the power 3 over 3 times 1 over 2, and integral of 7x minus 1 to the power 2 would be 7x minus 1 to the power 3 over 3 times 1 over 7. So this is what I mean by integral ax plus b to the power n. In all of these formulas, you can replace x by ax plus b, and you apply the same formula, but do not forget to divide by a, okay? So for example, the second formula, integral of 1 over x is ln x, ln absolute value of x. You can also write here a general form of this rule when you have 1 over ax plus b dx, and the answer would be ln absolute value of ax plus b multiplied by 1 over a, or divided by a. Here, for example, integral of ex is ex, so integral of e to the power ax plus b dx would be e to the power ax plus b, but divided by a. Here, for example, integral b to the power x is b to the power x over ln b, or integral b to the power ax plus, let me choose different number here, d, because I have b already, dx. So the answer would be b to the power ax plus, also let me change d because I have dx. Let me write it m, okay, plus m times 1 over a over ln b. So for example, integral 2 to the power 3x minus 5 dx would be 2 to the power 3x minus 5 over ln 2 times 1 over 3, because 3 is the derivative of 3x. So you can do this for all the rules by replacing. You can replace x by ax plus b, and then you will get the same formula, but you divide by a at the end. Also for the trigonometric integrals, for example, here integral secant ax plus b times tan ax plus b dx would be secant ax plus b times 1 over a. For example, integral cosecant square 5x minus 2 dx would be negative cotan 5x minus 2 multiplied by 1 over 5. All right. So I hope you understood this point. Uh, for 11, for formula 11, 12, you can uh, find these formulas. We illustrate how to find, how to prove these formulas. So if you don't want to memorize them, it's okay. For also 13 and 14, you can write tan sine over cosine and find this formula. Also cotan integral of cosine over sine, and then you take sine x as u, and du would be cosine x dx, so it would be du over u ln absolute value of u or ln absolute value of sine. So you don't have to memorize them, you can uh, immediately find them. If you want to memorize them for simplicity when they come as a part of the some difficult or long problems, then it's okay. The integral of sinh is cosh, integral of cosh is sinh, and this is also integral of x squared plus a squared, 1 over x squared plus a squared. We have seen that x squared plus 1 dx is tan inverse x, and now we are generalizing this formula. If we have a squared instead of 1, so we will have 1 over a tan inverse x over a. Also, we can generalize the formula that we know about sine inverse. We know that the derivative of sine inverse x is 1 over square root of 1 minus x squared, and the integral of 1 over square root of 1 minus x squared is sine inverse x. What happens if we have a squared instead of 1? We will have sine inverse x over a, and notice that there is no 1 over a multiplied by sine inverse x like the one multiplied by the tan inverse. Okay, now if you memorize all of these formulas and you are armed with these basic integration formulas, what to do when you have an integral. Okay, notice that integration is not like differentiation. When you have a question differentiate, you can immediately uh, know how to differentiate the function. But here it is not sometimes easy to find the integral. Okay, you need to think, you need to have a strategy to solve a question about integral. So first, if you have any of these formulas, immediately you use them. If not, then try these steps. Try first to simplify the integrand if possible. So for example, here, this question, square root of x, 1 plus square root of x, if you just multiply, if you expand, you get square root of x plus x, and now this is x to the power half, and this is x to the power 1, and you use the first formula, integral of x to the power n. So sometimes algebraic manipulation or using trigonometric identities will simplify the integrand. So here, for example, tan theta over secant square theta, if you write it, if you write tan as sine over cosine, and 1 over secant square is cosine square, and canceling cosine with one here, with one of these cosines, you get sine times cosine. And now you can take sine theta as u, and cosine theta d theta would be du, and then it would be u square over 2 or sine square over 2. But also you can use this formula. We know that sine 2 theta is 2 sine theta cosine theta. So sine theta cosine theta can be written as half sine 2 theta, and we said that integral of sine 2 theta is cosine 2 theta negative cosine, okay, because the derivative of cosine is negative sine. So over 2, because 2 theta over 2. So the answer would be 1 over 4, negative 1 over 4 cosine 2 theta over 2. So you can solve this question in two different ways. And of course, you can prove that the two ways are the same, but you need to change cosine 2 theta to sine theta. Uh, Also here, if you have sine x plus cosine x square, if you just simplify, if you expand this, then sine square plus cosine square is 1. And now you can solve this easily. Integral 1 plus integral 2 sine x cosine x. You can write 2 sine x cosine x as just sine 2x, and you find the integral, or also you can put sine xu. So simplifying may help. If everything is simplified, try to look for an obvious substitution, the usual substitution, taking u as g of x and noticing that the derivative of g of x should be in the integral itself. Okay, so for example here, if you just take u as x squared minus 1, then du is 2x dx, so I need 2 here and half outside, so this integral would be half times du over u, and then ln absolute value of u would be the answer. Of course, if you do not look for the substitution first, you may deal with this as a rational function and use partial fractions, a over x minus 1 plus b over x plus 1. Well, this is also easy, but somehow longer than the substitution. If you can solve the question by substitution, this would be usually easier for you, the usual substitution. If not, if you do not see a substitution in the question, then try to classify the integrand. Is it a trigonometric? Do you have trigonometric functions inside the integrand? Do you have sine times cosine? Or do you have tan times secant? Or do you have cotan times cosecant? Okay, if you have one of these three, then 7.2 will help you to solve the problem. If you have a rational function, uh, then 7.4 will help you to write the rational function as partial fractions if it's a proper rational function. If not, you use long division first. Integration by parts. Is it a product of x or a binomial or a polynomial times trigonometric function? Is it x times sine x or times cosine or times tan? Is it x times ex or x squared or whatever? Okay. Is it x cubed times ln x, for example? Okay. If it is one of these examples, polynomial or power of x times trigonometric or exponential or logarithmic, then immediately you use integration by parts. You take x as u and this as dv. Only here you take ln x as u and this as dv. Here you take x squared as u and ex as dv. Use integration by parts as we did in section 7.1. Now, if you have square root of x squared plus a squared, or square root of x squared minus a squared, or square root of a squared minus x squared, then you use the trigonometric substitution we studied in section 7.3. Here you take x as tan theta, here you take x as secant theta, here you take x as sine theta. So if you have one of these square roots, or even we said x squared minus a squared to the power 3 over 2, for example, you can also use 7.3. If you have an nth root of ax plus b, okay, then you can take it as u and use rationalizing substitution, which we mentioned in section 7.4. It may also work for nth root of g of x, this method. Okay, so this method will help you whenever you have a square root or a cube root or nth root of ax plus b in the problem. But notice that here x to the power 1. Okay, in general you can use it for g of x. If not, if the question doesn't have any of these forms, not trigonometric, not rational, not by parts, not radical, not radicals, so think of the problem again. Okay, but think again using the main two methods in substitution, the usual substitution, and by parts. These are the basic methods. So try substitution again. Okay, even if no substitution is obvious, like you said, like we have seen in step 2, try to use substitution. Okay, for example, substitution could help in solving problems that are not obvious. For example, let us talk about integration of x square root of x minus 1, for example. Here we will use substitution ux equals x minus 1 if we have the derivative of x minus 1 outside, but we have an x outside here. So substitution is not obvious for this problem. Although if you use u equals x minus 1 and find du would be dx, and change this integral from x to u, x would be u plus 1, and square root of x minus 1 would be square root of u, and dx would be du. You can solve this question easily now because u times square root of u is u to the power 3 over 2, and 1 times square root of u is u to the power half, and you can solve the problem. So substitution helped you to solve the problem, although it wasn't obvious that you can use substitution here. Or nevertheless, you can solve this problem in another way because you have a square root, so you can take it as you can use rationalizing substitution. So if you take u as square root of x minus 1 and then finding u square, and then you can change, you can find x, because you need x, it would be u square plus 1, and then you find dx would be 2u du, so you can change the integral. X as u square plus 1, and square root of x minus 1 is u, and dx is 2u du, so it would be also easy to solve. 2u square, so 2u to the power 4 plus 2u square du, and you can continue from here. So you can solve this problem in two different ways: rationalizing substitution or usual substitution. May you also, if not, if you cannot use substitution, try by parts. Okay, by parts will help in finding the integral of tan inverse sine inverse ln x. Okay, and somehow you can use it also in some other problems, not the one we mentioned here, not like this necessarily. Okay, but then you need to think again and again and try many times how to use substitution and by parts. Sometimes if you manipulate the integrand, if you multiply by the conjugate, it may helps. So here, integral of 1 minus cosine x, how can you find this integral? There is no way to find it. There is no formula. What can you do? But if you multiply by 1 plus cosine x over 1 plus cosine x, the conjugate of 1 minus cosine x, then you will get 1 plus cosine x over 1 minus cosine square, which is sine square, and you can write it 1 over sine square, which is cosecant square, plus cosine x over sine square, and then this one is easy. Integral of cosecant square is negative cotan x formula, and this one you can take u equals to sine x, then du would be cosine x dx, and you will have du over u square, and you can find it easily. Sometimes for difficult problems like tan square times secant, because this has power 2 and secant power 1, So if you remember in section 7.2, this is the third case. So you can write it as integral of secant cube minus integral of secant. And you know integral of secant cube and integral of secant from previous problems. So you can relate the problem to old problems. Sometimes you need to use several methods. You need to evaluate first by substitution, for example, and then you use uh, another integration, okay? Uh, Maybe by parts or something else. So you may use series of methods to solve the problem. Let us quickly try to use this strategy in solving these examples. If you look to this question, I have tan to the power 3 cosine to the power 3. What can you do? One of the things you can do here is just writing 1 over cosine cube as secant cube. And if you have tan cube times secant cube, then you can solve this problem using 7.2. If the power of tan is odd, then you take u as secant x and proceed like what we did in 7.2. Here, what can you do? Well, I have a root. I cannot find integral sine square root of x directly. So what can I do? If you take u equals square root of x, rationalizing substitution, then u square would be x and 2u du would be dx. So I'll have sine square root of x is u and dx is 2u du. So I'll have integral 2 times integral u sine u du, and now I can use integration by parts. Okay, I don't have to take it u here. You can call it, if you like, you can call it uh, w, for example. Okay, w. So keep everything w. So I can write it, I can take by substitution now u equals to w and dv equals sine w. I continue using integration by parts. Here I have a rational function and it's an improper rational function. So I use long division and continue uh, using section 7.4 partial fractions. If you look here, you notice that you have a usual substitution. If you take u equals ln x, then du would be 1 over x dx, and this would be integral du over square root of u. And you can continue easily. What can you do in this integral? Well, if you want, you can take the square root equals to u, but it would be somehow long. But if you just multiply by, because square root of 1 minus x over square root of 1 plus x, you can write it as square root of 1 minus x over square root of 1 plus x. And you can multiply by square root of 1 minus x over square root of 1 minus x. Or, I mean, you multiply by the conjugate of 1 plus x in the denominator. So 1 minus x over 1 minus x. Okay, it's the same, this one or this one. So I will have here 1 minus x times 1 minus x under the square roots. So I'll have 1 minus x, and here square root of 1 minus x squared. And now you can, to answer this problem, how to find out the derivative of 1 minus x squared is negative 2x. So if you just distribute and write it, integral of 1 times dx or dx over 1 minus x squared plus or minus, because there is a minus, integral of x over square root of 1 minus x squared, you will notice that the first integral is just sine inverse x, and this integral you can take u 1 minus x squared, and du would be negative 2x. So I need negative 2 and 1 over negative 2, and you find the integral using substitution. Let us finally answer this question: can we integrate all continuous functions? And uh, the answer to this question is no, because for some functions, the integral of these functions, like integral of ex squared, it has been proven that this integral cannot be written as uh, the elementary functions which we know. Elementary functions like logarithmic, trigonometric, inverse trigonometric, hyperbolic, inverse hyperbolic, polynomials, rational, all of these functions, if you try to write integral ex squared in terms of them, you will not be able to, because it has been proven, although using the fundamental theorem of calculus, this each any continuous function has an antiderivative, but this antiderivative doesn't have to be written in terms of an elementary function. For example, integral of ex squared, or all of these integrals cannot be written as the integral is not an elementary function, which means you cannot solve the problem using the functions you know. So pay attention that integration is not as easy as differentiation, and not any question you can solve. You have to follow the strategy to know the rules and try your best to solve the exercises in this course. Hopefully, you are good now with integration.